German, any language is welcome.
No, just Russian.
Betrachten wir.
Thanks for the invitation. I'm very happy to have a talk here. So, my name is Andronick Arutyunov. I will talk to you about derivations in group algebras. I see here two black boards. White.
No. This is the idea of High School of Economics. They were white, but English is black. So they step by step they become black. You see.
Okay. So I think that this one will be for algebra, and this one will be for geometry, because I will talk about one way to understand what is a derivation and the other operators which look like derivations in a geometrical sense. So what I'm going to talk about, well, and I understand that most of you are interested in common derivations for polynomials. I will talk about them also, but most of this science is interesting when the group isn't commutative. Well,
and look, in your coordinate system, algebra is much smaller than geometry. We like algebra.
Okay, then algebra will be here, and geometry will be there. Geometry is rather algebraic. It's not algebraic geometry, but the geometry is rather algebraic. Well, okay, let's start from the derivations. So today we will work with.
So that this is good.
This is good. Okay. Today we will work with the group G. It's finitely generated. I mean that number of generating elements is finite. And what I'm interested in group algebra, it's finite linear compositions. I mean the following, that it's zero almost always. So it is non-zero for just finite number of elements J elements from the group. So because Professor Arjantsov said not to talk about functional analysis, so these sums are just finite. I will not talk about functional analysis, but it's interesting when these sums are rows, and there is a little bit very nice science about this, but we will not talk about it. So what is the derivation? Derivation is a linear operator which acts in the group algebra. It's linear, and it must satisfy to the Leibniz rule. Everybody knows it from calculus, the first course. And of course, if you take as a group G abelian group, for example, free abelian group of rank n, then these derivations are well known. It just can be understood just as derivations for polynomials, but I said that it's much more interesting when group G isn't commutative. So, two examples. First one is inner derivation. So for A, an element from the group algebra, then inner derivation is maps x to the commutator. AX, it's AX16A. Well, I think that everybody knows about such derivation. And of course, the set of all derivations, it says Lie algebra. Sure, because if you take two derivations, you take their commutator, it's also a derivation. Of course, the composition of two derivations isn't a derivation, but the commutator is. And if a group is not commutative, then it's the one to don't commutate, so it's something non-trivial. So what I wanted to say that inner derivations, it is the set, it is generated by all inner derivations. It's an ideal in algebra of all derivations. What does that mean? I think everybody knows, but I will remind it to you that the commutator of derivation and arbitrary derivation is an inner derivation. So that means that it's an ideal. So important to say that I can factorize all derivations by inner derivations, because if you see an ideal, you must factorize by an ideal. Always. It's the rule. Most of math is about factorizing something by ideal or a normal subgroup. So we will call it outer derivations. So I will write out. Well, I don't write its outer derivations of what algebra, because we have in this talk we have fixed an algebra. We are looking for derivations just in this algebra. If there will be questions about what is going on when you want to compare derivations into different group algebras, then I will write this, but it will not be very soon. So we can change the definitions when it will be necessary. So, okay.
Let me interrupt you sometimes.
Sure.
Dear colleagues, this is a completely elementary object, so I hope that all of us understand perfectly, right? Certainly, we would prefer finite dimensional algebras or
No.
finitely generated algebras.
Finitely generated.
But this is okay. Your algebra is finitely.
It's finitely generated.
Group
here.
is finitely generated.
Yes, group is, so the two different dimensions, yes. Each is finitely generated as algebra. I mean that I can just take these elements, multiply them, and then I will get all algebra. But as a vector space, it's finitely dimensioned. Of course, if the group is not finite, and as we will see a little bit later, it's interesting that the group is not finite.
Finite. And
Finite, yes.
what about this in? This is SLE algebra. This is what? This is our associative group algebra, Lie algebra constructed from this modular center.
This one, inner derivations. Inner derivations, it's, of course, it is a subalgebra in algebra of derivations. It's not equal to the derivation, because if you take the central element of algebra, then the inner derivation is trivial. I think it's true that you can just take your algebra, factorize it by center, and then you will get inner derivations. I think it's true, but I'm not sure it's in this точности. Exactly, yes.
Okay, yeah. But this, it depends only on this associative algebra, so it should be
Yes.
constructed from this.
Yes. And little point that outer derivations are not derivations because they don't lie in the algebra of derivations. It's elements of factor algebra. But okay, anyway. So yes, and to what Professor Rajan said, you can ask the questions. I understand that my English now isn't very good. It will be better near the end of my talk. But right now it's not very good. But you can ask me questions in English or Russian, and please interrupt me if I'm talking too fast or not. Или не очень понятно. Okay, so we have got derivations, we have got inner derivations, we have got outer derivations. Everything is nice, but let's take another example. So this is inner derivations.
Can I ask you?
Sure.
Can you say anything about this algebra?
About outer
So this is
derivations.
a Lie algebra.
Yes.
Anything else?
Yes, a little bit later.
Maybe this is the main subject of this stuff.
In some sense. Yes, well, sure. How about inner derivations? Everything is, it's nothing interesting about them. Because inner derivations, you can check commutator of them, nothing interesting. And of course, the outer derivations, it's interesting object. It's much more difficult than inner derivations. So, I think I will answer your question immediately in the following way. I will give you an example of outer derivations. So, let's take tau homomorphism from the group G two complex numbers. Let's take a central element in group G. It means, for example, you can just take a lateral element. Then I will call it central derivations. It's derivations which maps like that. I must take an element J, and it goes to tau of J, Z. It's rather easy formula. Good question is why this derivation, if I will properly change the derivation, why this derivation isn't inner? Because perhaps one can find out an element A such that it's equal to some inner derivation. I will prove that this derivation is not inner, but a little bit later. Not inner. It's not inner. It cannot be inner if it's not driven. So, well, first of all, why is this the derivation? We just need to use the Leibniz rule. So, A of J-ish, it's what? It's now J-dash, Z. Okay. This is a homomorphism, so I can move it to the sum. So it's tau J, J, H, Z, use H, J, H, Z. Because this one is equal to the sum of these elements, because it's a homomorphism, to a group of complex numbers. So now we can see that we can write it in the following way: tau J, J, Z, H, because Z is from the center of the group, so it commutates with everything, plus J, tau H, H, Z. So now we can look again to the definition. So this is tau, which is a central derivation of element Z, this one. Multiply H, J, then tau Z from H. So Leibniz rule is okay, everything. It's just direct calculation. It's rather easy. I don't know why, but I didn't find the formula for central derivations in any papers before mine. I don't know why. Perhaps I didn't look for them very good, but okay.
But there were a paper which studied derivations of group algebras.
There are a lot of papers which study derivations in group algebras, yes. Of course, I didn't check them all. It's impossible because there are a lot of such papers, yes. Usually they study derivations for some specific groups, for example, Cherenkov groups. I don't remember what does it mean, but Cherenkov groups. And for coding theory, it's important to study derivations over finite groups when you take as coefficients not complex complex numbers, but for example, integers or something like that. But yes, there are a lot of people who was interested in the derivations. I don't know why I didn't see this formula. But
For finite groups, there is no such derivations because tau is trivial. Am I right?
sorry?
For finite groups, these
Yes.
derivations are
Yes,
impossible
yes,
because
yes,
tau is
yes,
trivial.
yes. And also is not just for finite groups, but also for FC groups, groups with finite conjugated classes, and in some other cases. But yes, well, another example, if you take a group G, you factorize it by its commutant, so you are looking on the derived subgroup. If there are no homomorphisms to complex numbers, so there are no such characters, editor characters count. So this is the reason why you can, if the derived subgroup is finite, then there are no such derivations, of course.
Cool. So you mean that quotient group is prime?
Yes. Yes, of course. So, okay, we have got an example of central derivations. Let's just take it. So, what are my purpose? First of all, I wanted to prove you that central derivations are not inner. And more, if you take the Z derivations, which is as a linear space, is generated by all central derivations, then this is a Lie algebra, which can be embedded in outer derivations. So it's not an ideal, but when you take this factorization, I will prove that it intersects with inner derivations trivially. So that means that all such derivations are embedded in the algebra of outer derivations. So it will be first interesting thing. If you can find non-trivial homomorphism tau, you can take just trivial element identity as element from the center. So you have got outer derivations. I will explain why the converse is also holds. If the algebra of outer derivations, not outer derivations, of quasi-outer derivations, I will explain what does it mean. If algebra of quasi-outer derivations isn't trivial, it's equivalent to the triviality of central derivations. So it's rather important. So this is our algebraic question. We want to understand something about central derivations, about inner derivations, and we want to understand the structure of these algebras. So the way to solve this problem, as it was presented in, well, of course I should say it in the beginning, that these results are based on my papers, or papers joined with Professor Mishchenko and Professor Stern from Moscow State University. And near the end of my talk will be results which are common with some of my students. Well, I will take it a little bit later, yes.
So you introduced this Z there?
Yes. Central derivations.
You told that this is the linear span of all derivations of that kind.
Yes.
Do you claim that this is the linear algebra?
Yes. You can just take a commutator of them, and you will also get central derivation. It's just
this is the computation.
Just simple computation. I didn't write it in my tablet, so I'm not sure. So I can calculate,
Okay,
but
okay.
it will take 5
That's
minutes.
fine. So this is a Lie algebra, and we embed it into this algebra.
This is a Lie algebra which is embedded in the algebra of outer derivations. Yes. So geometry is a little bit specific here because it is geometry of categories. So we need the term category is known to everybody.
Category, yes.
Yes, okay. So, I need, well, I have got a group, I need a groupoid. Not a common groupoid, it's called groupoid of adjoint action. So, I will call it gamma. So, objects of this groupoid are just group elements, and homes are pairs of elements.
But just a moment. Category, this is no, but groupoid, it's better to explain.
Okay, I will. Groupoid is a category where all morphisms are invertible, nothing else. Well, I understand, I will say. So, well, you can just understand it as this is a point, this is arrows. So, how this arrow goes from which element to which element. If here is written UV, then this one is the inverted U, and this one is the inverted. So, for each pair UV from Cartesian product is a morphism, it goes from one object to another object, which for which objects AB from them is not trivial. It's a content question.
A being lost is which element?
A being conjugated.
A being after.
Let's understand this. What I said just. It's not trivial if, only if, there exists T such that T8 minus 1 is B. So elements A, B are conjugated. It's equivalent. Well, why? Because I want to say that this is conjugated with this one. Oh, we can multiply here by B, multiply here by minus 1. It's similar. So these two elements are conjugated. This object as A, this object as B, they are conjugated by element B. And of course, there are a lot of errors between this A and this B, because there are a lot of ways to conjugate one element to get the second element. I will explain it a little bit later, more precisely, but before that we need to explain what is the composition here. So, if here I have got an arrow U1, V1, here an arrow U2, V2, then, and of course I need that they are composable. That means that U1, the one inversed, it's this element, target of this morphism is, as it is written here, U1, the one inversed. It must be equal to the source of this morphism, the two inversed. So, if this holds, then these morphisms are composable, and their composition is the following morphism: V2, V1, V2, V1. One can think that I lost here something.
You too.
Yes, but I didn't, because this term, this condition, means that knowing the composition, I can know and U2 also. And that also means that I can write this composition with the U2 but without U1, but it's not very interesting. So, theorem. It's a aggregated theorem that gamma is a groupoid. What I mean, first of all, it's a category. So this composition is associative. Phi psi kappa is equal to phi composed with psi kappa. Proof just by direct calculation is not interesting. And well, okay, you can.
But our map is just conjugation. It's trivial because the group is uncompleted.
Of course, yes. I wanted to say that, in fact, here is associative multiplication, so this is also associative. It's trivial and it's associative because group is associative, of course. And in fact, if you will replace the group by good semigroup, it also will be associative, and there also be this construction. Okay, yes, of course. I need identity morphism. So I have got an object A, which is the identity morphism. It's A here. If you compose this with any other morphism, it will be the same. And so this is that it is a category, and what I mean when I'm talking that it's a groupoid, that means that for each morphism from of M, there exists an inverse morphism to the backwards from home BA, such that composition phi1 is one object, the corresponding object. I'll just write the formula for it. So if you take this morphism, the inverted is a morphism which looks like
I'm sorry, I don't understand why do we use such strange denotations, because we can say that we map A to B, this is just conjugation as you explained. And so the third one is very clear that when you conjugate by an element, there is a conjugation by the inverse element, and you obtain the trivial map. Don't need any proof.
Your arguments, they don't include categories, groupoids, and this is a very important part of modern mathematics. So
yeah, you can use this groupoid, but maps are just conjugations. This is
yes,
okay.
of course, but we have got two whiteboards here. I'm writing on this whiteboard так, чтобы solve my problem from another.
okay. I'm sorry. Yes.
Of course, this is easy exercise for students on the second course. It's not difficult to prove the theorem. Interesting is another thing which I'll talk a little bit later, because before that I must say some other clear things. First of them is that my groupoid is disjoint unit, yes, of subgroupoids, which I mean that this subgroupoid, it is what are objects of gamma U are elements conjugated with U, and homes are on gamma.
So these are conjugacy classes, right?
Yes. Well, it's this one is J part J. It's the set of all conjugated classes. Oh, class of conjugated classes. Don't care. This is also trivial, but we will need it a little bit later. So, one more definition before we will return there. If you can go to a groupoid gamma, the character here, sorry, the character here is a map from morphisms to complex number, such that he of composable morphisms is the sum of the morphisms.
So what do you mean form of gamma?
All morphisms from groupoid gamma.
This is a group.
No, it's not a group.
Itself.
It's not a group.
From
Sorry, one moment. I mean that if I have got these two arrows, their composition is this arrow, then if I write here a number alpha, here a number beta, then I must write on their composition the sum alpha plus beta. It's very natural. If you see arrows, you want to write on them numbers. If you can compose these arrows, you want to summarize that numbers.
Yeah, this is just the set of all morphisms in the category.
Yes.
And to each such morphism, you want to
write on it some number, complex
to assign a
number.
number.
Yes, and when you take the composition, the composition must be the sum of these elements. It's very natural construction. But I need not all characters. I need just locally finite characters. What does that mean? That means that for each v, he of uv is equal to 0 almost always. For almost always, I mean that there's just a finite number of elements u such that he of uv, of morphism uv, is non-zero. This is locally finite. It is x of gamma. This condition looks a little bit strange right now, but it will be clear in 2 minutes. And also, I need x0 of gamma. It's all characters such that they are trivial on loops. That means that if you take phi from loop, and the morphism, then phi of it is 0. Of course, it's not trivial right now that such characters exist or something like that. I will give examples a little bit later in 5 minutes. But
At least 0, 1 exists.
sorry?
At least the 0, 1 exists.
0, of course. And something more interesting.
I have a stupid question.
Sure.
Why do you say that this is geometry?
Yes,
Because
exactly.
in my opinion, this is algebra. I don't know. Geometry is some variety, some
You
set
see-
of points.
See, arrow.
Arrow is algebra.
We see error always come here.
Well, in fact, a little bit later, I will rewrite this. I will go from category to graphs, and there will be more joy. Well, we can put a joke on our seminar. What is non-commutative geometry? It's everything about which was written in Alan Kahn's book, Non-Commutative Geometry. This book looks like that. It was written there about everything, so everything is in non-commutative geometry. Categories also.
Okay.
Well, I'm saying that it's geometry because here works a geometric intuition. you take sums, and a little bit later we will work with graphs. And working with graphs, it's absolutely geometric constructions. But there will be no manifolds, nothing like that. But there will be a little bit of coarse geometry. So, main theorem. There is one-to-one. There is one-to-one corresponding between locally finite characters and derivations. And it can be given by formula. If U is element from group algebra, so we say that it can be written as a sum. G is from the group. Then you can write a derivation, and because it's a linear operator, you can write it as follows: sum, the GH, then the H, G. This is just a formula for linear operator. And amazing is that if you take a map here, which maps an element JH to this VJH, it's a character. And this is a one-to-one corresponding.
So D is a derivation, right?
Yes.
So you construct a map from the right to the left side.
Ask a question in 2 minutes. I will explain this again, and perhaps I will answer it. So what I mean, if you take a character here, you write that it maps JH to the number. So this is a value of the character on this morphism, and you put this value to this formula, then it will be a derivation. Another, if you take a derivation, you can write it as a linear operator, so you can find out here some coefficients, and these coefficients, which if you map to them from this morphism, it will be a character. It's one-to-one. So how it works? The Leibniz rule is equal to this condition. And locally finiteness of the character is equal to what? That this sum is fitted. Almost all these coefficients are trivial. And locally finiteness of the character is, I think, is clear. How to prove this theorem? In fact, it's not very interesting. It's just a direct calculation again. So, did I answer your question or not?
So actually, I don't understand what's going on inside the brackets. So, what is lambda? What is the power of lambda?
My writing is not very good, also as my English is. I will rewrite it. Summa.
So this sum is over the whole G, right?
Yes. DGH, lambda HG. This is sum by H. This sum is by G. What is written here? U is an element of group algebra. This lambda are coefficients of H in group algebra.
That's G, DHG. This
G
is a scalar, right?
Sorry?
This is a scalar.
Yeah, this is a scalar,
I see,
yes.
I see.
Yes. This is a complex number. This is elements of matrix of linear operator. If you take a group G as a, if your group G is finite, then these are just elements of the matrix of linear operator, because derivation is a linear operator, so its coefficients are this one. Because, well, if group J is not finite, then I don't know which is a non-finite matrix, so it's just coefficients of linear operator.
That's fine.
We can prove this theorem, but it's not very interesting. It's just calculating. You take these elements, you write what is the Leibniz rule, and you see the connection between these coefficients for U and V, and that's all. Nothing more interesting. But it's much more interesting to return to our examples. For example, for inner derivations, what's going here? Let's take an element of a group. So the character which corresponds to this derivation, to inner derivations, looks like that. You must take an object A, you must take arrows which go from it and write on them +1. On the arrows which go to A, you must write -1. On all other characters, you must write 0. How to see it? Just look to this formula. You understand, well, why? Because when you take a commutator with an generating element, so you have got there just two elements, one with plus, another with minus, so it's rather clear. And what's about central derivations? That's interesting. You must take an object Z. If you take an object in your groupoid, which corresponds to the central element, then its conjugacy class is trivial. It's just this element. Central elements are conjugated just with them. So there are no arrows from Z to other objects. And how look here and then the morphism? It looks as follows. Z, G, G, where G is an arbitrary element from a group. You must just map it to the tau of G. So this is the character. This is the character on this subgroupoid. Now it's trivial. No, central derivations are non-inner because all inner derivations are trivial on loops, and central derivations are not trivial on loops. So the intersection is trivial. Now it's ambitious. And well, we had got a question. I don't know how to prove this in another way. But now it's time for a question. We see that all inner derivations are trivial on loops. They are from this example. So perhaps you think which I will say to you that this is an equivalence. So all trivial on loops characters give us by this formula an inner derivation. But no, it's not true. And it's a very strange thing. So I want to give one new definition. I will say that a derivation is quasi-inner if such derivations, that the corresponding character is trivial on loops. So, looking here, we understand that all derivations are quasi-inner. But I will prove it a little bit later that not all quasi-inner derivations are inner. And before we will prove that, I want to say you one more interesting thing, that quasi-inner derivations are also an ideal. So the remedial in algebra of all derivations. And it's very interesting because, of course,
and the quotient will be isomorphic to the central derivations, right?
no,
No. Okay.
not enough. But of course, central derivations are embedded not just in outer derivations, but also in quasi-outer derivations. But well, I can explain why right now. What we have got several groupoids. For example, we can have a conjugated class which has not one element but two elements. There's a theorem of Usin, as I remember, that there exist groups with any conjugated classes of any number of elements. It's geometry or algebra? Geometry or okay, algebra. If I take element U such that its conjugated class, for example, consists of 3 elements, it's enough to consist of a finite number of elements, but more than one. So it's not an element of center. Then what looks like your groupoid? It has got 3 objects. You can write on these arrows whatever you want. It doesn't matter because it's not a finite number of them. You can take, for example, you can take the centralizer of this element. You can write a homomorphism to complex numbers. You can write these elements on these arrows as I did it here. And then you will have a derivation. And it's not central derivation because the support of this derivation is not one object. Understand? Yes? But of course, this case where you have got such derivations, it's specific. You must take some specific group, some very specific group. Another possibility to have non-central derivations I will explain a little bit later. I have defined what I mean by quasi-inner derivation, and
there is another question. So, are you able to describe the image of this set of central derivations in out? So, do you know exactly the subset of out, which is?
Let's formulate several questions. One of them is yours. What is the factor quasi-inner by inner derivations? Yes? And what is quasi-outer derivations? It's all derivations by quasi-inner. This is a very nice question because the answer on it to answer this question, I need coarse geometry. I need the number of ends of a graph. And I will explain it right now on that geometry desk. And this, one can understand what's the answer right now. It is a subspace of the direct sum of how to write it? Yes, okay, I'll write it like this. This is the sum by centralizers of elements, different centralizers. This is a set of all additive charities from the centralizer to the group. And this is not all such elements give you a derivation because it can fall to be locally finite, that character. Sometimes it falls to be locally finite. And I don't know a good answer when it falls. I have some examples, but I think we will return to this a little bit later. Before that, we will.
What is the sign here? So is it
This?
a subset? Yes.
Subset, yes.
Subset.
So before that, we will return to the geometry. Хотя нет, тут не нравится, что геометрия. Но, but anyway, well, I will talk in Russian. We have got a groupoid.
This is a good experience to speak English. I see that members of our seminar, they start speaking English better and better. So I strongly recommend you to use this possibility.
Yes, when I'm going to the conferences,
And this is
on the last day of the conference, I had to talk in English very good. So I prefer to have a talk on the last day, because in that time my English is perfect.
This is my main conference and your talk is the last.
Yes, but from the other see, it's first. Okay, so I want yes. Before this, another easy example before graphs. If J is abelian, it's as I said, it's the case when you calculate derivations on polynomials. Then all derivations are central. When they're of G, it's just central derivations. There is nothing else. That means that you can write any derivation in the following way.
So there are no inner derivations.
Sorry?
There are no inner derivations.
Yes. There are no inner derivations, and all subgroupoids have got just one element in subgroup. Just one object, yes. They are monoids. So every element goes where? Scalar product, well, no. I must say that G is a direct sum of its subgroups, primary, and then G goes to S. G? Not G. Well, this is a. This is a character. This is my element. This is a central element. And all elements are settled in abelian groups. So that's it. So why we discussed it on multiple readings? This science is not very interesting. For this science, abelian groups are not very interesting because everything is central. There is nothing else. But it's rather interesting to think what will happen if you take coefficients not from complex numbers or something like that, but the reformulation of this theorem to for normal people is following. All derivations on polynomials are partial derivations or their combinations. There are no other derivations. So there are no any other linear operator which will satisfy to the Leibniz rule. Okay, so graphs. How can we find a character? Because of this, well, okay, no, another way, I'll just give the definition. If you take a group G, then its conjugacy diagram is the graph which looks like as follows. So I need a set of generators, and you have got for two objects, for 2 points, A and B, an arrow which is labeled by X. It means that B is X inverted AX, it's just conjugated. this is not a groupoid, of course. This is just a graph. But you can see this graph in your category. And if you have got a character on the category, then you have got a character, some function on this graph. And backwards, if you have got a function on this graph such that for any way the sum is here, it's
Cyclically.
yes. If you take the composition of characters on these morphisms, then it must be equal to the character here. Each such character can be pushed up to the character on the groupoid. So, what I want to say, if you have got a character from x0, from x0, then how it looks for this graph? The following condition holds. No, before another thing. If you have got a graph and you have got a character on it, then it means the following. There exists a function p from objects to complex number, such that, for example, here phi, I have got an arrow phi, I have got here objects a and b. Then phi of phi is p of b minus p of a. This means that to look on characters from x0, it's equal to look on such functions. But we must understand what means that this character is locally finite. That means the following. In terms of this function p, of this function p, for almost all objects a, b, before that, for each generator x, for almost all objects a, b, such that they're x labeled way from a to b, it follows that phi of it is 0. No.
Do you want to take a mission?
No, yes. P of A is equal to P of B. So if P here and here is equal, then the character here is 0. And one can think that, so that this means that P is equal almost everywhere. But no, you can take integer numbers and right here, for example, 1, 1, 1, and there everywhere 1, here 0, 0, 0, 0, 0, and so on. And this character, this function p, will be like that. It's equal for almost all neighborhoods. But it's not trivial always. And what I want to say, for a graph gamma, the number of ends of graph gamma is the following thing. You take your graph, you cut off bounded sets, and you calculate the number of unbounded components. So it's maximal of unbounded components in gamma with B, where B is bounded. For example, for Z as a graph, number of ends is 2. Why? If you cut out something bounded, you have got 2 rays, right one and left one. If you take, for example, such graph, oh, you have got vertices here, you can cut out like this. You have got two unbounded components, but you can cut off a little bit more, and then you will get three components. So here are number of answers of 3. And if you take z by z, when you cut out something bounded, you have got always one unbounded component. And what is interesting, that
So what do you mean by bounded?
for graph just finite, it contains just finite number of vertices.
Because bounded might be understood in another sense of finite radius or finite diameter. This is different. From
I'm
finite.
talking about unbounded components, so it doesn't matter. You can cut off just balls, no problem.
You can have, I don't know, infinitely many vertices and a complete graph with a set of vertices. Everything is connected with everything. In one sense, this is finite. In other sense, this is not.
Okay, I'm talking about locally finite graph. So each vertex has just finite number of neighborhoods.
Then maybe this is it.
Yes, okay, yeah. I understand what you're talking about. It's really important, but I have a very good graph. Right.
20 minutes.
Sorry?
20 minutes.
Okay. The theorem.
I propose to erase something.
I will write it here, the dimension. But now I will write here some.
No, Andronick, this is important. We should understand the result. So if this is a theorem, please put it separate and we
Okay. Theorem. If you take quasi-inner derivations, which supported in one subgroupoid, if you take inner derivations which supported in that groupoid, then the dimension of this is equal to the number of ends of the corresponding conjugacy diagram minus 1. Example. Well, everybody knows what is the Leibniz and what is the derivations. Example, if you take a Heisenberg group, union matrices 0, 0, 0, APC, and you take a non-trivial element, for example this one, then if you take, if you look on conjugacy diagram of this element, it will be just a line as it was there. So that means that the space, linear space, of factorization of quasi-inner derivations by inner derivations is one dimension, and they will write a formula for this derivation, but don't think about this formula. I just want to explain it, how it looks like, because it don't look like interesting. So the plus is maps matrix to watch. This is 1 minus 1 or 0, and what I want to say, first thing is the following. What are quasi-inner derivations? In fact, each quasi-inner derivation, if you look here, is a sum of inner derivation, but this sum is infinite. This is not a sum from the algebra, it's formal sum. Because you can just take a potential here 1, here, everything over there. Here 1, you can take some of them and you will get this. But this sum is formal. It's not assumed in group algebra. You cannot summarize it like that. This is first thing. The second thing, you can calculate this factorization on each component if you know how it looks like that conjugacy diagram. How looks this conjugacy diagram? Partial result that if you take an important group, then its conjugacy diagram is a Cayley graph for factor group by centralizer. If you take other groups, that conjugacy diagram looks like very strange. I have got a hypothesis that here of SKU is 0, 1, 2, or infinity. It cannot be 3. This is a hypothesis. One my student says that it is true, another says that it's not true, but no one of them didn't prove it. So the part about derivations now can be stopped because I explained to you that if you want to study derivations, you can take the following construction. First, you must look on inner derivations, then you have to look on quasi-inner derivations, and you know how it looks like the factorization quasi-inner by inner derivations. It can be written in terms of that graph, conjugacy diagram. And how look like quasi-outer derivations? I also explained that. You have to take just your gamma u. You can have to take an object and you have to look on the centralizer of this object. And characters on this centralizer can be rewritten for all objects, and you don't care what is written here on arrows, on horizontal arrows, because you have factorized by them. Because the factorization by quasi-inner derivations means that you are not interested in what is written here. You are interested just in this. And that means the following. Another theorem. Quasi-outer derivations are not trivial. Non-trivial. They cannot be empty. If and only if central derivations are not empty. So if you have got a central derivation, then okay, it's not trivial. But if you have got a quasi-outer derivation, which has a separate notch and one object, then that means that you have got a non-trivial additive character on the centralizer of some element, and it can be pushed up to the non-trivial homomorphism from the group to the complex numbers. That's the second thing. If I have 20 or 30 minutes.
May I ask you? So at the beginning you told us that all central derivations cannot be inner, right?
Yes.
But another question, can they be quasi-inner?
No.
Also no.
Also no, because quasi-inner derivations are trivial on loops. Central derivations are not trivial on loops. So they are also embedded in quasi-outer derivations.
There is also an inclusion like this for quasi-out derivations.
Yes, we can write here.
Yes.
Sure. If I have 20 or 30 minutes,
I'm sorry, but
I would care to talk about homologies here, but in fact it's not interesting because it's not important for this. If I have got 10 minutes, I can talk about some other possibilities of this method. Because there are some other cases when we can work in the same way. I have got 10 minutes.
10 minutes.
Okay. But if you have got questions about this, you can ask me right now. Perhaps we can talk about it a little bit more, if you want, if you're interested. You are not interested, okay. Very nice. Finish the geometry. And finish another group with another groupoid right now. So, I said in the beginning that you can look not just Leibniz rule, but there are some others. Well, let's take lambda and group action on itself, and let us look on operators of the following u alpha v. Here's the multiplication plus u v multiplication inverted from u inverted multiplication alpha of u. Looks strange, yes?
So
But
what is it?
What
is it? So
this is a Leibniz rule. Странно, что вы не узнали. What is written here? If you have got two elements in a group algebra, of course. Well, in
what do you mean
group,
by alpha? So alpha is lambda?
alpha is a linear operator which maps group algebra to itself, yes, of course, as a for derivation. If you take generators u and v from a group, you can multiply them. You can map by alpha somewhere, and perhaps this action is such that this rule holds. Well,
Does it involve the action lambda? No.
yes, this is here is lambda. This here, lambda is here.
So the action of the element
Yes.
v to the minus 1
Yes,
on I.
yes, yes. Example. Lambda is, if lambda maps JH to JH, what we will see here, this one as it was, v minus первый, its identity, u inverted, its identity.
So if the action is by just conjugation, then we get the usual.
Yes, and if we take the conjugation, we will take just Leibniz rule.
So this is just a generalization.
Yes. And what I want to say to you, that if you take a groupoid, again groupoid, objects are group elements, and the composition will be here as, and arrows look as follows, from M to J of M by, it means that this is a pair of M, J. It's another notation that, like it was. Then I want to say that all such each such derivation, each such operator is equivalent to some character of this groupoid. I'll just write you a formula. Alpha of G, it's sum here H G J H. I want to say that okay, theorem for each alpha exists character He such that it can be written in the following way. Why it's interesting? Because this is a Fox derivation. If here somebody who likes outs, then you'll know what is this. It's Fox derivations. And it follows 5 or 10 minutes of talking again, something like this, and then it follows that there are a lot of Fox derivations which are quasi-inner, but not inner. Inner Fox derivations are common Fox derivations, and there are some others. And what is interesting that these characters are characters on a Cayley graph. Before that, for Leibniz derivations, it's characters on conjugacy diagrams, and for Fox derivations, it's characters on Cayley graph. Another example, you can look on twisted derivations or sigma tau derivations. What does it mean? That the UV, it's the of U sigma of V plus tau of U del of V. Here sigma tau are group endomorphisms. I will not take your time and explain which groupoid you must to take here. I'll just say that if sigma tau are group endomorphisms, not just group algebra endomorphisms, then they can be described in the following sense. And you can look on characters, you can look on inner and quasi-inner derivations, and so on. Another interesting thing is the following. We know Lie structure on derivations. It's just commutative. But you can translate this structure to characters. You will get a rather easy formula, and that means that for sigma tau derivations, for characters of them, you also have something like Lie algebra structure. This is a nice question because we tried with one of my students to write it, to understand what it means, but we didn't get a nice formula. So one can try this. It's, I think, rather interesting. Well, my colleagues who are interested in sigma tau derivations said that it is interesting. But for me, sigma tau derivations are not interesting. So, last thing, what is the big fish here which we can try to find? The big fish is following. I think that if you take an arbitrary associative algebra and you are interested on how it looks like derivations of them, then I think that the answer is following. You must find some category, not a groupoid. It will be not a groupoid, it will be a category. And locally finite characters on it give you derivations on your algebra. I don't think that it is true for all associative algebras, but I know that it is true not just for group algebras. I know that it's true for 2 examples of semi-group algebras. And I think that it is true in much more general case. What's also interesting, another interesting thing is looking on these conjugacy diagrams and comparing derivations on 2 different group algebras. This thing has a coarse sense. It is a coarse invariant. What I mean, there is some construction which is called coarse mapping, coarse equivalence. When you look on it, it doesn't feel inner derivations because they are local. It doesn't feel quasi-outer derivations because they are also local. And this thing is what they sense. So, what I think that if you have got 2 mostly equivalent groups, then this part of derivations is similar, nothing else. But it's another problem, and I don't have good answers on it, and I'm working about it right now, or not right now, tomorrow. I will be working about it tomorrow. So I think that I will finish here.
Okay, thank you very much.
About coarse geometry another time.
But immediate question. I'm sorry, but presentation was not really systematic. Can you summarize? So it was a question about derivations of the group algebra. So what do we know now?
We know now the following. You have got an ideal of inner derivations. You have got an ideal of quasi-inner derivations. We know what is a factorization of quasi-inner by inner. Diagram, conjugacy diagrams, number of
So
elements,
some
and so on.
constructive description of this factor.
Yes. As constructive as it's possible.
Okay.
We have good understanding what means quasi-inner derivations. You must look on centralizers, you must look on the additive characters to the group of them, and they give you all such derivations. Not all such characters give you derivation because it can fall to be finite sums here. You must check it, and I know how. And I don't know how to check it, and I don't think that it's possible to check it, in fact, in some combinatorial terms. But for if you give me a group, it can be checked rather easy. And here you have got a very good and very nice subalgebra. It's a subalgebra of central derivations. They are very nice. You
Not here, but complementary to
you have got them as a subalgebra here.
here.
And here, at the outer derivations, it's more interesting that he also here.
This is
And
about
it's
algebra.
it's not trivial when central derivations are not trivial. Another question: when outer derivations are not trivial, they are not trivial when they are not trivial, or this is not trivial. And to check this, it's easy. Well, sounds easy. You just have to look on your graph and to calculate the number of ends. It's rather easy to understand for concurrent group if there are two ends or infinite ends, or if there's one end. So you understand everything about this, if it's trivial or not, and you can look on derivations from here, but they don't look nice. Formulas are very strange here. You know almost everything about this. You can calculate them and so on. So, for derivations, these are main results. We have got good description and good decomposition. And what I want to say that this decomposition to quasi-inner and quasi-outer derivations is much more geometric than common decomposition, because it's easy to understand what is inner derivations, but it's very hard to understand what is outer derivations, because you have got there elements of two different senses, this one and this one. One can say that it's very easy to understand what's inner derivations, and it's not easy to understand what are quasi-inner derivations. But I want to say that I have cleared it, but you have got, if you have got a character which is trivial on loops, then it is given by potential, and potentials are good described. You can understand what potentials you have and so on. And if you have got a potential, you have got a formula for the derivation. Well, this formula was written how? I just looked on the conjugacy diagram. I have written the potential, and then I calculated by a formula. The formula is not very nice, so I will not write it on the desk, but it's easy to understand.
Okay.
So it follows from this one. So,
Okay, next question. Do you have some types of groups? Say, your central derivations, this is a concrete formulas, right?
yes.
Do you have some types of groups that you say, if group is of this type, then all derivations of the group algebra are given by some concrete formula?
Yes. For example, important groups of rank 2. For example, Heisenberg group.
You can describe all derivations.
Yes. There are central derivations and some this type derivations and inner derivations, nothing else. There are no quasi-derivations and so on. Also, I have did it for the case of some finite groups with coefficients not from complex number but from finite fields, because it was interesting for some colleagues who study cryptographics and so on. So they were interested in how look like all derivations when group is finite, something of like permutations and so on. Well, I'm answering your question. So I know how to calculate them. For some, the main problem is the following. It's rather easy, rather hard to understand how it looks like a conjugacy diagram. The problem of conjugacy is a difficult problem. So why it's easy? Why this problem is solved for important groups of rank 2? Because because I proved that conjugacy diagrams there are coarsely equivalent to Cayley graph of some group. I think that this problem is solvable for other important groups of different ranks. You have just to take the extension and so on. In other cases, in fact, I didn't think, because it's, for some reasons, it's not very interesting. It's much more interesting to understand the coarse type of conjugacy diagrams. And we had some problems with this, and so we're solving a little bit another problem. Well, I think I answered.
Okay. Do we have any more questions?
I have one. Why do we study group algebras? In two reasons, in my opinion. First of all, it's an interesting examples of algebras and just to have examples of algebras. And another, the first maybe reason is that we are trying to understand something about the group, knowing something about the group algebra. So this is the way to investigate a group. And you said that you hope that some results from group algebras can be extended to results for more general algebras. And my question is there a hope to investigate groups knowing something about derivations on its group algebra?
First of all, I had other purpose. I think that I know everything about group.
Yeah, I
so
understand.
I want to understand something about derivations. Another way, I'm not sure that it's well, first of all, I don't know. Secondary, I think no, because in this approach, group structure is much more interesting to explain the group algebra, and I don't understand how to map the group algebra conditions to the group. I don't see that. I don't see that way. But perhaps perhaps it is. Again, why I'm interested in group algebras? First of all, because this construction works, so we see that we can describe derivations as characters on a groupoid. Working with some semigroups which look like group, for example, multiple semigroups or inverse semigroups, they are similar to group. We see that there are something like that. You again have a category or a groupoid, you have got characters, and these characters describe you all derivations. For some reasons, I think that if you have got, if you have an associative algebra with good basis means that multiplying basic elements, you will get again basic elements, semigroup algebra. I think that for such algebra, it's possible to describe all its derivations as the characters of some category. But why I am interested in that? Because I'm interested in pseudo-differential operators. And to calculate pseudo-differential operators on non-compact manifold equipped with an action of a group, you in fact need to understand what's going on with derivations on such group algebras. But this is absolutely another history. I will not talk about it right now. But my motivation is from, I often sorry, from functional analysis.
Okay. So any more questions? If not, then I will ask also two questions. Didn't you try to apply your information about derivations to a description of automorphism group algebra?
No. I think it's possible, but I didn't do that.
And then a question not related to the talk, but this is about general education, I don't remember. There is some big open question concerning group algebras. Something like if you have an element of finite order in your group, then you have zero divisors in group algebra. And
Yes,
whether it's true or not.
Kaplansky conjecture, there are several of them. As I understand, it's unknown whether the group algebra has or doesn't have zero divisors.
No, the question, let me formulate. You have a group, and you know that it has no elements of finite order. Is it true that there are no zero divisors in the group algebra? It looks very naive and elementary, and this is open for many years.
Yeah, well, you can just Google Kaplansky conjecture for group algebra. There's three of them, I think.
Yes, there are some beautiful questions about group algebra.
Yes, and that means that group algebra is not very easy object. They are very strange, because to understand whether you have in a group elements of finite order, yes, and Google it. For group algebras, yes, it's a...
Okay, let us thank Andronick. I don't remember whether we... Thank you very much for your talk.